work. Uh, the step size for elephant random work is not fixed, but it's a random variable. Uh, this talk is based to paper work with Xiequan Fan. He's a professor at the University Bahia City. I Jian Hu, she is my colleague in here. Yeah. Flora Levi, she is a professor at the University Bahia East. And Qinghuangdao, he's a professor at the Southern University for Science and Technology in China. My talk including 5 parts. The first part, I will recall the classical model elephant random work, the definition, and some related work. And the second part, I explain our model, elephant random work with random step size. And the third part, we present some recent work for elephant random work with random step size. And the fourth part, we just give a sketch for a proof for climate moderate deviations. And in the last part, we talk about some future work, if the time is allowed. For the first part, we recall the classical model elephant random work. The elephant random work was first introduced in 2004 by Suze and Tramples. In this model, the people study the memory effect of a non-Markovian random work. The models can be described as follows. At the very beginning, the workers at the position T0, the T0 equal to 1, it means at the origin. At the time n equal to 1, which means at the first step, the elephant move to 1 with probability Q, move to -1 with probability 1 minus Q. It means he moved forward with probability Q, move backward with probability 1 minus Q. This is the first step. Now, after the first step, the position of the elephants is denoted by T1, and T1 is equal to X1. X1 is a random machine with parameter Q. At the time end, the step xn is determined. It's determined by the following method. First, we choose the integer n prime from this set 1 to until n minus 1 is uniformly. Xn is determined stochastically by the following rules. Xn equal to xn prime with probability p. Xn with minus xn prime with probability 1 minus p, which means with probability p, we reinforce the one step before. With probability 1 minus p, we reduce one step before. So, for n larger than 2, the position of the elephant is given by the following formula. It's given by Tn. Tn is the summation of xi. Xi is defined by this formula. Xi equal to alpha I minus x beta I. Okay. What's the definition of this alpha n and beta n? Okay. Alpha n is defined like this. Alpha n is a random machine distribution with parameter p. P belong to 0 and 1. And beta n is random uniform distribution on the integers from 1 to 3 until n-1. Moreover, alpha n is independent to x1, x2, xn, and beta 1, beta 2 are also independent, and also they independent to alpha n. Okay, this is the definition of elephant-Ladon work. The elephant-Ladon work has motivated many interesting work. For example, Bertrand, they establish some connection between the polyartiac and elephant-Ladon work, and they establish some functional limit theorems. Galati and Gaff and Schulz, they prove central limit theorem and a strong invariance principle for elephant-Ladon work when the parameter p belong to 0 and 3 over 4. And they also show that if p is larger than 3 over 4, then the elephant-Ladon work converges to a non-generated Ladon variable, and this Ladon variable is not Gaussian. Baku, he introduced the martingale approximation to study the elephant-Ladon work, and he recovered the many classical results for elephant-Ladon work, like almost full convergence, central limit theorem, also the scaling limit for p larger than 3 over 4. There are a lot of results in this paper, and also I benefit a lot from these papers. With that, Guaza, this guy, he established almost the central limit theorem. Our team may be more interesting on the normal approximation for such type models. We focus on the relative error and absolute error for the normal approximation. In this paper, we established the climate moderate
Please, just can we
the climate
can you
moderate
switch off
it's
microphone?
about the okay, sorry, it's about the relative error for the normal approximations. In this paper, we consider the convergence rate for elephant-Ladon work in the Wasserstein-1 distance. Recently, Bertrand, he studied the memory effect and the parameter p, how the parameter p impact on the passage at the origins for the elephant-Ladon work, which means when the parameter p changed, how many times the visiting time for the worker, visiting time for the worker at the origin, I think. Sometimes it's also called recurrency properties. Except the original elephant-Ladon work, there are also many variations for elephant-Ladon work. For example, Becky, Lucille, they introduced a multi-dimensional type elephant-Ladon work. They established some almost full convergence and multi-dimensional central limit theorem and so on. Good start to emulate. They introduced several kinds of generalization, include the two-type generalization in the model, in the new model. The elephants only remember the very beginning part of the step or very recent part of the step. See also August and Al-Mashikuhi for the worker only remembered the some part, some recent step. Rollins, he also introduce some asymptotic analysis for the reinforced elephant-Ladin work models. A more recent work maybe come from Cheng and Rollins. In this paper, they introduced amnesty reinforcement for the multidimensional elephant-Ladin work, and they established something like almost full convergence, moderate deviation principle, weak invariance principle, and so on. Okay. Recently we introduced a course is also a variation for elephant-Ladin work. We call this model elephant-Ladin work with random step size. This model can be described as follows. The model is very close to the previous. For enlargement tool, we instead of fix the step size, the position of the elephant with random step size at the time n is given by Sn equal to summations of yi, and yn is defined by this formula. Yn equal to alpha n times x beta n times Cn, where Cn is a sequence of positive IID Ladin variables with finite means. If the mean is not equal, moreover, the mean should not be equal to 0. Otherwise, this is a totally new model. The variance on the J is finite. Moreover, the step size Ci is independent to alpha I and xi. As we can see that if Jn is strictly equal to 1, then this model become the classical elephant-Ladin work. As we can see that in here, alpha n is the absolute of alpha n is equal to 1, and the absolute of x beta n is also equal to 1. So the absolute of yn is equal to the absolute of Jn. So we call Jn the step size. Okay. Without loss of generality, we may assume that v equal to 1, which means v is the mean of J1. We assume that equal to 1. Otherwise, we can consider the case as n over v, because after normalize, we always can take as 1. And also clearly, if sigma equal to 0, which means J1 equal to 1 with probability 1. So when sigma equal to 0, the elephant-Ladin work with random step size reduced to the usual elephant-Ladin work. The following result is we have the following result. The first result is about the lot or interleaved logarithm. For the usual elephant-Ladin work, the lot or interleaved logarithm is established by Beck. I think we can find this paper. Can you see this paper? I think I'm not sure. Sorry.
Yes.
Okay. Because here I have been covered, I cannot see this one. Sorry. We have the following result. Assumes that p belongs to 0 to 1. The variance of J1 is finite. If p belongs to 0 to 3 over 4, then the shift limit of this one is bounded by these quantities. if sigma equal to 0, this result almost reduced to the result of BQ, but BQ this one is not less or equal. Indeed, he proved that this is equal, but I do not know how to how to prove this to equal. When p equal to 3/4, then this one limit is equal to square root 2, almost surely. When p belong to 3/4, 1, it means p larger than 3/4. The Sn our this quantity is converging to a Ladin variable L. L is not generated non-Gaussian Ladin variables. And this Ladin variable is indeed is exactly same to the limit of elephant Ladin work. Okay, this is the first result. As we can see that if p larger than 3/4, we do not have center limit series because this limit does not converge into a normal Ladin variable. So my study will focus on the case p larger than 0 and less or equal to 3/4. For p belong to 0 and 3/4, we introduce the following two sequence. An is defined by this formula. Vn is the sum of ai squared. An and Vn, somehow this formula is complicated, but they are positive sequence. In the papers of BQ, they prove that An satisfied these equalities. So from this equality, we know the An is grows like n with power 1 minus twice p. Okay, this is the order of An. For p belong to 0 and 3/4, BQ prove these equalities. From this equality, we know that Vn is in order of n with power 3 minus 4 times p. Okay. For p equal to 3/4, Vn is it grows like log n. This is some well-known result for the two sequence An and Vn. The second the second result is about the center limit theory. We assume that the variance of J1 is finite. Then we have the following center limit theories, which means Sn our this is converging to normal distributions in distribution. Here Sn dit equal to An multiply Sn minus twice q minus 2. This part indeed is some bias of this one. No, I think yes. Just for center this part. Center for center this one. Okay.
Sorry. Here there is no L missing in the expression of Sn.
Sorry.
Here there is no L missing in the expression of Sn. Sn may be An Sn with minus 2q minus 1 multiplied by L or not. There is no L.
No, Rafiq, because it is in the diffusive case. It's not in the super diffusive case.
Okay, thank you.
Okay, yes, exactly. Yes. But yeah. Thank you for the explanation. So this is center limit theory. Sometimes we also interested in the convergent rate, which means we are interested in the absolute error for the convergent rate. Sometimes it's also called Barry-Essen bond. the carbohydrate maybe they have a lot of distance. One is called clocomorph, second Westerstand, also Zelister. Okay. First we consider the distance of clocomorph. For a real Ladon variable x, we denote the kx. Kx is defined by this formula. It's the clocomorph distance between the distribution of x and the standard normal distribution. The third result is about the coverage rate for elephant Ladon work in the clocomorph distance. As I told before, we focus on the case P less than 3/4. We have this coverage rate when the elephant Ladon work. Okay, this is for elephant Ladon work. That's not including the Ladon step size because Tn is the usual elephant Ladon work, as we did know before. Let me see. Sorry. Yes. Sn is for the elephant Ladon work with Ladon step size. And Tn is for the usual elephant Ladon work. Okay. Sorry, I should not look at delta. I think it's Sn is the, no, because Sn is here. Sorry. This An multiply Sn. Sorry, it's here. Okay, it's correct. Sorry. This is for the usual elephant Ladon work. Now we have this result. And this give an estimation for the absolute error for normal approximations. This is in these orders, which means the order should not be better than 1/√n because this is a classical order for symmetric Ladon work. For symmetric Ladon work, the best coverage rate for clocomorph distance is 1/√. So we cannot much better than this one. Okay. And this part is indeed something really depend on the elephant Ladon work model. Okay. From this coverage rate, we can see that if P is less than 5/8, the coverage rate is 1/√n. When P larger than 5/8, the coverage rate is 1/Vn, and Vn it's in these orders.
Can you, Xiequan, can you recall? I forgot the definition of mu n.
Mu n, Vn. Oh, you okay?
Yeah.
Vn definitions is given by this one. The
Okay.
sum of AI squares, and his order is given by this formula.
Okay.
Okay. So we obtain this coverage rate. Okay. This model is for centroid because this is a BR here. Indeed, it's here. Okay. For non-centroid quantity, An times Tn over square root Vn. For this quantity, we have the following coverage rate. The coverage rate is in this order. As we can see, this is no 1/Vn. It's 1/√Vn. It's not as good as this one because this one does not have a square root. From this coverage rate, we see that when P less than half, then the coverage rate is 1/√n. When P larger than half and less than 3/4, the coverage rate is in this order. When P equal to 3/4, the coverage rate is in 1/√log(n). Okay. the last theorem is for the for the elephant-Ladon work. Next, we consider the elephant-Ladon work with Ladon step size. For elephant-Ladon work with Ladon step size, we have this coverage rate for Kolmogorov distance. We assume that the Z1 has a finite moment of order 2 plus low, low belong to 0 to 1. Of course, it works for low larger than 1, okay? But for low larger than 1, we can always take low equal to 1. The following inequality holds, which gives this one. As we can see, this coverage rate indeed equal. It's come from the general Ladon work. For the general Ladon work, his coverage rate in Kolmogorov distance is 1 over this quantity. This part is indeed is somehow depend on the really depend on the models. This is one Kolmogorov distance that we consider the coverage rate under the zero to leaf distance. First, we recall the definition of this distance. The leaf distance of order art is defined by the following formula. For two probability measure mu and v and early r larger than zeros, then the leaf distance of order art is defined by this formula. Here we should explain lambda r. What's the lambda r? Lambda r is defined as follows. We denoting the L, the natural integers satisfies this one, which means L is the integral part of R. Lambda R is a class of real function f, which are L times continuous differentiable, and such that this regularity condition holds. Of course, this is defined the leaf distance for two measures, but for Ladon variables, we can also define his zero to leaf distance. It's defined by this one according to the distribution. Okay, defined by the distribution. For this distance, we have the following two results. First, if R belongs to 0 to 2, we have this inequality false. This one, of course, is about the elephant Ladon work with fixed step size or general Ladon work, general elephant Ladon work. Sorry. This coverage rate indeed is the same to the classical coverage rate for Ladon work, general Ladon work under the Z-list distance with order art. When Z1 has a finite moment of 2 plus low, in order of 2 plus low, low belong to 0 to 1. We have more general result. It's like this one. This is for the zero distance. For the Wasserstein distance, we also have some similar result. First, we recall the definition of Wasserstein distance. We denote the L mu v being the set of probability lot on R2 with marginal distribution mu and v's. And the Wasserstein distance of order R. It's defined by these formulas. If x and y are random variables, we can also define his his versus stand distance by binary distributions. Okay. It's non-net for R belong to 0 to 1. The lift distance and the versus stand distance are equal. So for R belong to 0 and 1, we do not need to study the quadrilet because these two theory already given the quadrilet under the WR distance for R belong to 0 and 1. So we only focus for the case R belong to 1 and 2. We assume that Z1 has a finite moment of 2 plus rows for a constant row belong to 0 and R. No, we have this quadrilet for the elephant random work with random step size. So as we may interesting for the case R equal to 1. Okay, so we take R equal to 1, sigma equal to 0. What can we obtain? If we take R equal to 1 and sigma equal to 0, we have the following quadrilet. Okay, here if we take sigma equal to 0, then an times Sn become to an times Tn. This is a bias indeed here. This one is also Vn, so it become an times square an times Tn over square root Vn. Here, okay. We negative the PR part maybe it's not here, okay. But no, we have this quadrilet. We just how can we get it? For example, we take R equal to 1 because for the usual elephant random work, we can always take row equal to 1. We take row equal to 1, R equal to 1, and this is 1 over square root n. Okay, and this is 1 over Vn. But because this has a BR, it's twice Q minus 1 over square root n. So the quadrilet indeed is depend on this BR. It's a quantity over square root Vn. So so for this part, for this no centrally the quantities, the quadrilet become this one. Okay. This one indeed is come from this bias is here. It comes from here. From this term. Sorry. Plus Q is minus 1 over square root of Vn is come from these terms. Because this term is much larger than this term, I think. Okay. It's much larger than this term. So for usual elephant random work, the quadrilet in versus 1 distance, it's in these orders. It's 1 over square root n plus 1 over square root Vn. From this result, we see that the 1p smaller than half, then the quadrilet is 1 over square root n. And this quadrilet is the same to the classical quadrilet. When p larger than half, less than 3 over 4, the quadrilet is this order. When p equal to 3 over 4, the quadrilet is 1 over square root n, square root log n. It's in this order. This result somehow slightly improve my previous result, because my previous result we have additional factors. Indeed, we have log n here. For example, when p belong to 0 n, belong to the interval 0 to half, and the coverage rate in this paper it's log n over square root n. But right now I remove this log n. Okay. And the last theorem is about the climate moderate deviations. The climate moderate deviation is for the relative error for the normal approximations. We assume that this condition is satisfied. This one. This condition is called Bornstein conditions. It's called Bornstein condition. Indeed, this condition equivalent to the condition that the moment generating function of J1 exists is equal to these conditions. Somehow like Poisson distribution or normal distribution, they also they satisfy these conditions. Under these conditions, we have the following result: when p belong to 2.5, then the relative error for normal approximation is given by this formula. Because this is the Taylor probability, and this is the Taylor probability for the normal distribution. And this is the Taylor probability for the elephant-Lardon work with Lardon step size. So when we divide this is indeed is a ratio. We take a log n, which means the ratio, how the ratio is close to 1. When p is belong to half and 3/4, then the relative error is given by this formula. Okay, when p is equal to 3/4, the relative error is given by this formula. Okay. For the proof, okay. For the proof, indeed, I only give a proof on the climate moderate deviations. I mean, I only give a proof for this series. And for the proof of calculate in Kolmogorov distance, what's the stand distance? There are two methods. One is Lindeberg's method. Second is Stan methods. But I'm not trying to talk about these two methods. I only talk about some climate moderate deviations. Okay. In this, I try to give a sketch how to prove climate moderate deviations. At the beginning, we introduce the filters. We take F1 is the trivial sigma fields. Fn is defined by this. Okay. We find that an times Sn minus these quantities can be expressed in this form. This part indeed it's just, as we know, the Tn is the elephant-Lardon work. So this part is only depend on the elephant-Lardon work. The elephant-Lardon work with random step size. Okay. No, sorry. I made mistake. It's the elephant-Lardon work with fixed size on the classical elephant-Lardon work. And this part, we can see that if we condition this part, which means alpha I and beta I are fixed. Now this part is also become fixed, is either equal to 1 or either equal to -1. Anyway, this is like general random work. Okay, because Ji minus 1s are RID sequence and centered. We introduce the filtrations. F0 being the trivial filtration. Fk is defined by this. Is k larger than 1 and less than n. It's defined by this formula. So under these filtrations, this part indeed can be lightened sum of martingale differences. For k larger than n, less than twice n, I define fk by this formula, which means we condition this part, and also added some condition for some how to say the some information for ZI, so that this part can be also written in form of martingale differences. Indeed, we can see that this part indeed is martingale differences. It means this part. So these quantities can be written as a sum of martingale differences. And now we scale it, we normalize it by some factors. Sorry, I lose some bias. I lose the this term. Okay, but it's a positive numbers. It's not so important, I think. Sorry. I think I should add it. My mistake. Sorry. I should add this quantities here. Sorry. Okay. It can be written as a sum of martingale differences. Okay, Cursi Ni is defined by this one. We can prove that the Cursi Ni is satisfying the conditional Bornstein conditions, which means these conditions. Here the epsilon n is given by these formulas, and his order can be estimated. For the conditional variance, we can show that the conditional variance for these martingales converging to one with very high probabilities. Indeed, they converging to one very fast. It satisfies these formulas. The delta n, his orders is given by this formula, which can be calculated. Then we prove Kalman model deviation for general martingales. We prove that for general martingale differences, if it satisfies the condition A1 and A2, these two conditions, then we can establish Kalman model deviations in this form. So with this result, we just applied this lemma to these models, to this. So we obtain the Kalman model deviation for elephant random walk with random step size. Here I want to talk some about future work, because in this model I assume that the random step size is IID, but maybe other people may consider something median case. For example, the step size maybe it's not an IID random variable, maybe something alpha median, beta median somehow. Okay. Also, one may assume that the random step size is something like Markov chains or stationary sequence. Then we can also obtain some result. Of course, this is a new type of models. We also can study the functional center limit theory for elephant random walk with random step size. Indeed, I obtained the function center limit theory for elephant random walk with random step size, but the functional is a new type. We may also work for almost sure center limit theories. Strong approximations. For strong approximations, we obtained such data for elephant random walk, but not yet for elephant random walk with random step size. We may also study the extreme value theories. This is new because without the random step size, we cannot works extreme value theory. Okay. Sorry. This is all my talk. Thanks.
Thank you very much, Xiequan. Thank you very much for this very nice talk. Is there some question or some comments?
Yes, please, Mohammed.
Rafiq?
Thank you, Xiequan, for your nice talk. And thank you for accepting to talk in our webinar. In your model, is it the same model if we replace X alpha I, Z I by directly Z alpha I? That means that the size of the step is a random variable, and at any step, the elephant remember an antecedent step, and he makes the same step with the probability P, or minus this step with the probability 1 minus P. Is it the same model or is different?
Sorry, I did not catch your idea. Sorry. Okay. I think you took this one. Okay.
Yes. If I take Yn is Z alpha I, alpha N. Yn is Z alpha N. Okay?
Z alpha N, sorry, Rafiq, Z alpha N or Z beta N?
Sorry, alpha N, Z beta N. Alpha N.
Okay, okay, yes.
Good question. Thanks. I don't think so. It's different. I think this is new models. It's
Yes.
not same to me, I think.
Because you introduce some kind of dependence again.
Yes.
So seems to be different.
It's different, I think. It's totally different. Not same to this one. It may be much more complicated, I think.
Okay, thank you. And your sequence Z I are integers or not, or just positive real numbers? Zi, the sequence Zi, the values are integers or not, or real numbers? You understand my question? What?
Okay. Sorry. Sorry. I did not hear. Pardon.
Zi are integers, random variables or not, or just real?
The values of the random variable Zn. It's an integer values.
Or not this?
No, necessarily.
No. Ah, okay. Maybe.
Yes, it can be a continuous random variables.
Ah, okay.
When the distribution is continuous, no decrease. Okay.
Okay. In your theorem one, in the theorem one, super diffusive case. Okay, here.
Yes.
Case 3i. There is no results about the fluctuation. In other words, there is no results about the limit in distribution of Sn divided by n to the power p minus 1 minus L multiplied by something.
I mean, I think you means the distribution about L. Is that?
Not the distribution of L, but the limit in distribution of the difference of Sn divided by n to the power Tp minus 1 minus L. What about the limit of the difference? In your result, in your theorem, you...
Then there's no difference. Indeed, it's exactly in the same one. Okay.
Okay, but maybe Sn divided by n to the power Tp minus 1 minus L multiplied by some sequence converge in distribution to central limit theorem. Like
yes, exactly. If indeed there's some result. I forgotten the exact paper of Becky. I think some people Becky proof that if Sn our Ln times this factor, minus some properly scalar, maybe we also can obtain some center limit series. Okay, because this is a diffusion path. It grows really fast. We should divide this part. Okay, we should drop this part, and after drop this part, the remaining is still Gaussian.
Okay. Yes. Can you go to the slide 14, please? 14.
Okay.
Yes, yes. Here. Okay. And in the equation 3.7, the denominator goes to infinity. It's okay. The denominator, yes. It's okay. It goes to infinity. So
yes, sure. Yes, sure.
So what is the utility in the expression of S tilde n to have minus 2q minus 1? Since 2q minus 1 divided by square root of nu n plus n a n square sigma square goes to 0. I think that there is no difference between S tilde n and a n s n.
I agree with you. Sure.
Okay.
Because this quantity is always goes to infinities when p
yes.
belong to this range. Okay. Yes, I totally agree with you.
Okay. Slide 18, please, and the last question. 1a.
Okay.
In the definition of Zolotarev distance,
yes,
there is no absolute value listed here.
No.
Not the supremum of absolute value of the difference of integrals.
It seems not necessarily, probably. I see.
Okay.
Yes, because this quantity probably should be always larger than 0, I think. That's right.
Okay, thank you again, Xiequan. Thank you for your
Thank you for the question.
Thank you, Xiequan. Is there another question or comments? No? Xiequan?
Sorry,
yes.
Mohammed. Sorry. There is a question. In the same slide here,
Okay.
There is no R missing in the left-hand side before the last line. Not the last line, but the line before.
Okay.
At left, no. Slide 18, 1.8.
1.8, okay.
Okay. The not the last line, but before.
In the inequality.
Yes, inequality. At the left, we have no R, and on the right, we have R.
Well, sure. No.
Before the line before.
In the inequality, but yes. I think it's not.
No, sure. No.
18. Sorry, 18. 1,
80. Yes, 80. Yes.
80.
Yes, 18. Yes.
In this line, not the last line, but before the line before.
Before.
In the right.
It is maybe Rafiq, you mean in the definition of lambda R.
Okay.
Definition of lambda R here.
Yes, the definition of lambda R.
Yes, sure. You means here. Okay. Yes, definition of lambda R. Yes. Sure.
Yes, but the question of, if I understand, the question by Rafiq is in the inequality, when in the definition of lambda R, in the left-hand side of the inequality, there is no R, but I think it's not a problem, Rafiq. It's the definition of.
Maybe, but no? R is between L and L plus 1. And L and R are integers. So necessarily we have R equals to L plus 1. You understand?
Yes. Yeah.
R is between strictly larger than L and smaller than or equal to L plus 1. And R and L are integers. So necessarily R and L are equal.
No, because R is fixed, is a positive integer. It's not an integer.
Not an integer?
It's
no,
not
it's not in integer.
uh,
No.
maybe it's not integers. Yes.
Okay, okay.
Can be any values.
Oh,
Okay,
it's
I
not in
understand.
integer.
Okay, thank you again. Thank
Okay.
you.
Thank you. Yes.
Okay. Xiequan, I have some question. Okay, I had some question already asked by by Rafiq, but if you come back to slide 12.
12. Okay.
Theorem
Okay.
1. I just want to come back to the question by Rafiq about the super diffusive case. It means
Yes.
when P is larger than 3/4.
Yes.
The Sn here, if I remember, is your variation of the elephant random walk. I mean with the random step size.
Yes. With
Okay.
step size.
So in the classical elephant random walk, in the classical model,
Yes.
there is a result not by Berku in 2018, but by Kubota and Take in 1 year later. And
Okay.
they obtained the fact that the fluctuation of Sn divided by n to the power 2p minus 1 are still Gaussian around the random variable L. It is exactly
yes.
what Rafiq told you.
Yes.
When you center Sn normalized by n to the power 2p minus 1 by L,
Yes.
then it still converges to some
Normal
Gaussian.
variables.
Yes.
Yes.
So, did you do you know if there is an extension of this result by Kubota and Take in your model?
No. 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 It's still an open question.
It's still an open question.
Yes. I believe we can obtain same result. Okay. I think we should obtain.
I think it's a very interesting question. And another question is the question of the rate of convergence, even in the classical model, even in the Kubota and Take result in the super diffusive regime.
Yes.
I don't know if the method you used with Jérôme Dedeker and Florence Merleved in order to get your result on the rate of convergence can be useful in the super diffusive regime, because if I understand, you did not obtain a rate of convergence when P is larger than 3/4. Only when P is only in the diffusive regime. You obtain your result also in the diffusive regime when P is less than 3/4.
Thank you. It's it's a very good question. I'm also very interested in this question, but I did not consider it, so I cannot give you an answer. Sorry.
Okay.
I did not consider this case.
I would like to, if you can recall, in which case you obtained with Jérôme and Florence, in which case you obtained your result on the rate of convergence for the Kolmogorov distance in the diffusive regime.
Yes. Only work for diffusion regions.
But what happened when P is equal to 3/4 in the critical regime?
It's belong to the diffusion regions.
When P is 3/4, you get some result on the rate of convergence?
Yes.
Okay.
It's okay. 3/4 is okay. But larger than 3/4, I know little.
It's an open question. Okay.
Yeah, it's an open question.
Well, okay. Can you come back to slide 15? 1.5.
Okay.
Yes, in theorem 3. Okay, it's a very nice result. The proof is not simple at all. And my question is about the optimality of the rate of convergence you obtain.
I think this one it should be optimal. I believe.
Yeah, what you believe?
I believe this coverage rate is optimal.
The bound you obtain is optimal.
Yes, I believe it's optimal.
Okay, because when p is less than you obtain a critical value here. It is a 5/8.
Yes.
Okay.
Yes. Because in this proof, I used somehow 5-term Taylor expansions. 5 terms. Because we usually only use the 3-term Taylor expansions, but we use the 5-term Taylor expansions. So I believe this one it's optimal.
You believe that the result is optimal?
Yes.
But you don't have a counter example or a proof of.
I did not
this.
prove this. No, I did not. Indeed, there's no control example because this is the example. Sorry.
Okay, I understand.
But maybe we can carefully verify the detail of the pool to see if this coverage rate is exactly optimal or not. But I think it's optimal.
Okay. Okay. I have just last question.
Okay.
It's not really a question, but a comment on it may be very interesting to extend also your model to the multidimensional case, like in the thesis by Lucille Lolin.
Yeah, exactly. You are right. Sure. I think this is important because for me, you note in the real world, the step size cannot be fixed. Indeed, usually it's something it's randoms. So I think we should do it. We should do it.
Okay. Okay.
I'm also going to propose a project working for for such type extension.
Okay, thank you very much, Xiequan. Is there any question, comments?
Just the last question, Mohammed, please.
Okay, Rafiq.
If you can go to theorem 1, Xiequan,
Okay,
please.
01, okay.
Second case.
Second case, okay.
Yes. If we normalize the second case, we have not some limit distribution of the normalization. Normalize, that means that absolute value of Sn divided by the denominator minus square root of 2 multiplied by something cannot goes to some distribution.
No.
Maybe or no.
Maybe note. I don't know. Maybe probably note because I think in this couch sometimes this result already given the couch rate for Sn. I think. I'm not sure for it.
Okay.
I did not see such type of result because I think usually it's not. I don't know. I'm not really sure about it.
Okay, thank you.
Okay, thank you very much.
Thank you.
If there is no more question, we can thank the speaker again. Thank you very much, Xiequan.
Thank you also. Thank you, Professor August. Thank you.
Thank you. Thank you, Muhammad.
Okay, thank you.
Thank you. Yes.
See you next time. I don't know who is the next speaker. Next time.
Just a second, and I give you the answer, please. Okay, next time. Next time, 26 March at 3:30, Bastien Melin of Laga, Institut Galilée, University Paris 13, France.
Okay.
So 26 after 2 weeks.
Okay, thank you very much. Thank you again, Xiequan, and we get in touch. We
Yes.
have a lot of things to do on the elephant random walk.
Yes, thank you. Also, you may visit my university if it's possible.
Okay, thank you very much. Bye. Bye, Rafiq.
Bye. Bye.
Merci beaucoup.
Yes.